Welcome back. So, in the last snippet we looked at an adiabatic turbine. We have already looked at an adiabatic compressor as far as its HS diagram goes. Now, we will discuss it in slightly greater detail. So, we will again draw the HS diagram for a compressor, which is as follows. We draw the HS diagram and we show the two isobars. So, this time we realize that the inlet to the compressor is actually a lower pressure, and the compressor is used to pump the fluid from the lower pressure to the higher pressure, and hence this is Pi, which is the inlet isobar, this is Pe, which is the exit isobar. This is the inlet state, let us call it I. Ideally we would have gone vertically ahead here, that is at the same entropy as the inlet we would have reached, let us say it is E star, that is our nomenclature, it is E star. And what happens is, if it is an actual process, you actually go in this fashion, that is you go towards an increasing entropy and you reach the state E. So, this is the actual state, this is the ideal state. E star is the state where the entropy is the same as that of the inlet, whereas E is the state where the entropy is more than that at the inlet. So, we can write down the same equations that we had done for the turbine. In this case, we will see that Pe is greater than Pi, because this is a compressor. Se star of course is equal to Si, which is the inlet entropy. Now, in this case Se, that is the actual exit state, is greater than Si, which implies Se is greater than Se star. Let us put it as greater than or equal to, because it could still be ideal in some cases. So, in this case, in a compressor, the enthalpy at the exit is higher than the enthalpy at the inlet. So, He is definitely greater than Hi. What of course we can notice, that because of the nature of the line, because of the nature of the isobar which keeps on increasing, an increase in entropy implies that He exact, that is He actual, is greater than or equal to He star. So, now if we look at the difference He minus Hi, because He is greater than He star, we will have He minus Hi is greater than or equal to He star minus Hi. Of course, now if we look at our first law for open systems, it is W dot S is equal to M dot Hi minus He. Now, Hi is a smaller quantity than He, and we are going to get that W dot S is a number which is less than 0. It is a negative number, which is correct, which is what we expect. The work is input into the system. W dot S, the shaft work, is a negative quantity. If we look at the definition of W dot S, because both quantities are negative, and because He star minus Hi is of a larger magnitude, if we consider W dot S actual, we will realize that W dot S algebraically is a smaller quantity than W dot S star. This is algebraically. Both of these are negative, and W dot S is a larger negative quantity than W dot S star. But if one looks at only the magnitude, then W dot S, that is the actual work input into the system, is greater than or equal to W dot S star. So, in this case, if we look only at the magnitude, this is what is happening, that the actual work input into the system is greater than the ideal work that is expected to be put into the system, and this is what we expect. We are trying to put in some work to get a particular result. That is an ideal case, we expect something, and because of so called irreversibilities and the process being non ideal, we have to now put more work into the system, and this is what is being seen here. W dot S is greater than equal to W dot S star, and because of this nature we define the efficiency slightly differently to ensure that the efficiency is a number which is less than 1, and also you will realize that it is intuitively a correct way of looking at efficiency for a compressor. We define the isentropic efficiency NSC for the compressor as equal to W dot S star, notice that now this is in the numerator, upon W dot S, and since both of them are negative, the efficiency is a positive quantity, and since magnitude wise W dot S star is less than W dot S, this is a number which is less than or equal to 1. This is the so called isentropic efficiency of the compressor. Of course, you can also see that you could have written it as H E star minus H I upon H E minus H I in this case. So, this is true for this case. In general, we will say that it is the ideal work that is expected to be input divided by the actual work that is input. So, this is how the efficiency is defined for a compressor, for an adiabatic compressor, and it is called the isentropic efficiency for the same reason that we have based the ideal work input into the turbine based on an isentropic process. Thank you.